Hello, this is lecture 10. Last time we started chapter 11, where we were comparing the means of independent normal populations with the same variance, and this gave us the z-test and the t-test. So in the z-test, the standard error is just what you would expect, so sigma square root of 1 over n plus 1 over m. For the t-test, however, we used a pooled standard deviation, which we derived last time. So the pooled variance is given in the formula here. It is a weighted average of the two standard variances depending on the degrees of freedom of the sample variances, and this gave us a t-test of where the test statistic was degrees of freedom n plus m minus 2. Today we're going to continue section 11.2, comparing the means of independent normal populations with different variances. I should mention that we're going to come back after the midterm to 11.2, 11.3, and instead of assuming that our populations are normal, we are going to we're going to do a non-parametric test. So that is going to remove that assumption, and that will be coming after the midterm. We're also going to do power calculation today and look at comparing the means of paired samples, in which case the assumption of having independent populations is removed. Okay, so section 11.2, we now remove the assumption that we have the same variance, and it's natural to look at the sum of the sample variances divided by n and m in this case, which turns out to be an unbiased estimator. It's just what you need. So you can check here that its expectation is the variance of the difference of the means. And what is miraculous is that the test statistic that you would form in the null hypothesis, where you assume that the means of x and y are the same, turns out to be a t-distribution, and the degrees of freedom is what's highlighted here. So I don't really have a good intuition about any meaning of this degrees of freedom. It's something that you don't remember but can look up if needed, or if you need to calculate it, that can be programmed into R very easily. So we looked at an example where we have, where we're going to do a statistical test, a two-sample test. Here we have 50 rats randomly divided into two groups of 25 each. The rats in one group were given steroids. They were timed running a maze. The rats in this non-steroid group, or the control group, had an average time of 10 seconds with an SD of 2 seconds, and the rats in the steroid group had an average time of 9 seconds with an SD of 5. So we can see right away that the SDs are different. So we are going to be in the second category now, where variances are not assumed to be the same in the two populations. So what's the SE of the differences of the two averages? So that's just following the formula that we just derived. We calculate the test statistic, testing the null hypothesis that the steroids make no difference. So here I decided to do a two-sided test, but you could do a one-sided test if you wished. And the test statistic in this case is what's shown here. And what is the p-value? So to compute the p-value, we would need to know the distribution. We need to know the distribution of our test statistic. And so that is going to be the t-distribution with that crazy formula for the degrees of freedom, which turns out to be 31 degrees of freedom in this case. You can check. And so we need to find the areas in the tails to the right of 0.93 and to the left of 0.93. So that's just 2 times p norm of minus 0.93, which is 0.35. Assuming that alpha is 0.05, we would not reject the null, and hence we don't have evidence that steroids make rats run any differently than non-doped rats. Then we moved on to power, and so it's important when you're designing an experiment to have a large enough sample size so that you'll be able to reject the null if there is a statistically significant difference. So let's see here. So to make things simple, we're going to assume a bunch of stuff here. Sigma is known. Sigma is the same in both populations. We're assuming here that we have a normal distribution, and N and M are the same size. N is large enough, we're going to do a z-test. So the alternative here is that the difference of the means, we'll call that delta, is positive. So you can see here our rejection region is in blue, and the power is shown in red here. So that's the area under the H1 curve in the rejection region. Alpha is the area in the rejection curve under the H0 curve. So we can compute power in this case in terms of the CDF, and you can check the effect of increasing delta, alpha, sigma, and n on power using this formula, or I think it's just more intuitive just to make pictures, and you can see that the power increases in all cases except sigma when sigma increases, in which case the distributions become more overlapped. So you can see that the area in red decreases. Okay. So here's an example of doing a power calculation, and this is very straightforward. So we're just solving for n. So power is given by the formula we just derived, and you're solving for n by basically taking the inverse CDF of both sides of the equation. Okay, so I think at this point we took a break, so I will